Advanced Math, Lesson 32. Inverse functions, the four quadrant signs. My book's crooked. Okay, inverse functions, the four quadrant signs, inverse trigonometric functions. Inverse functions really aren't that hard. And we'll start with a nice, easy linear equation. So they give us the equation y equals 2x minus 1. Go to our work paper. And if we remember, a function is kind of like an answer machine. We plug in data into our function, we get an answer, right? So this is telling me the graph of a line. If I want to see where the line is when x is equal to 2, I plug in 2. I find out that 2 times 2 is 4, 4 minus 1 is 3, so the y-axis would be 3. So when I plug in the number 2, I get the answer 3. So at x equals 2, y would be 3. That gives me a point on the function, right? So that is a function. So we'll go ahead and graph this and see what happens. So that's 1 point. So I did at x equals 2, y is going to be equal to 3. I can also use my y-intercept, -1, and I know that that's going to be a point on the graph. And then I'll do one more for good measure. I already did 2. Let's do -2. If I plug in -2, -2 times 2 gives me -4. -4 plus -1 gives me -5. So I go -1, 2, 3. Wait, hold on. Sorry. Let me pause. I think I made a mistake. Yep, yeah, I did. That's +1. Okay. That's -1. That's my y-intercept. And yes, if I plug in -2, I get -5 for y. So -1, 2, 1, 2, 3, 4, 5. Now I've got 3 points. I've made sure I know where my line is going to be, or where my function is going to be, right? So let's talk about an inverse function. So this is y equals 2x plus 1. We'll put this off to the side for a second. Now, to find an inverse function, all we have to do is we take our function y equals 2x minus 1, and we switch the x and the y. So I rewrite this equation as x equals 2y minus 1. Now, after I've switched places, I want my function to be set equal to y, right? So all I have to do is solve for y again. So I'll go ahead and subtract 2y from each side to move it back over to the other side. I get minus 2y plus x equals -1. I want the x to move, so I'll subtract that from each side. So now I've got -2y equals -x minus 1. Excuse me. And then last thing I'm going to do is I'll divide by the coefficient of -2. The negatives cancel, the negatives cancel. So then what I actually get is y equals 1/2 x plus 1/2. Now let's go ahead and graph this line, or this function. So we know that our y-intercept is going to be 1/2. I can go ahead and put 1/2 as a point on my graph. What if I plug in 2 again? So at 2, x would equal 1, and then the value would be 1 and 1/2, right? So at 1, 2, I get a 1 and 1/2, okay? And then at -2, I'm going to get -1 here. -1 plus 1/2 would just give me -1/2. All right, so I've got this line, which is a little bit shallower, right? And at first, this doesn't seem to be anything special, right? This line and its inverse don't really seem that special. There doesn't seem to be a clear relation between them, right? So now we've got y equals 2x plus 1, y equals 1/2 x plus 1/2, until we look at the graph of y equals x. Now, the graph of y equals x is a perfect diagonal line that runs across the coordinate system right here. You know what? I'll put this one in orange so we can see the difference. Now, do you see what the graph of y equals x does to this inverse relation, or these inverse functions, yeah, you should be able to tell that they're both perfectly dissected by the middle ground, or the perfect function of y equals x. And so that's what inverse functions do. They are definitely split and separated. They are exact opposites, but it's hard to tell at first until you look at the base equation of y equals x. Same thing with quadratics. At quadratics, you'd probably look at y equals x squared, and then the inverse functions would then reflect off of that one. So inverse functions aren't hard. All you do is to find them, you switch the x and the y, solve for y. And then that goes for every x and y. If you have an equation that has two x's and one y, both of those x's become y, that one y becomes one x. So it's just an even trade. Everything that was an x now becomes a y, everything that was a y now becomes an x. So finding inverse functions isn't that hard, and then graphing them isn't very difficult either. Next, our lesson talks about the 4-quadrant signs. That's just the signs of positives and negatives in the 4 quadrants of the coordinate system. And we talk about that with the unit circle, so I'm not going to spend too much time on that. What we are going to talk about, though, is the inverse functions of cosine, sine, and tangent. These also have an alias, or another name. So what we're actually talking about here is the functions of sine -1, cosine -1, and tangent -1. There's another name for these. These are synonyms. They mean the exact same thing. It's just two ways of writing one idea. So instead of writing sine -1, people will commonly write arc sine. Instead of writing cosine -1, people will commonly write arc cosine, or they'll refer to them in speech, or the arc tangent. And what they're simply saying is the sine to the exponent of -1, or the cosine to the exponent of -1, or the tangent to the exponent of -1. This is called the inverse function because it's the exact opposite of what sine, cosine, and tangent do. I'll use a reference triangle to demonstrate this. So let's say we have our 30, 60, 90 triangle, right? We have root 3, 1, 2, our 90-degree angle. If we were to take the sine of 30 degrees, that would equal the opposite over the hypotenuse, right? 1 over 2. So sine of 30 degrees equals 1/2. So the ratio of 30 degrees is going to be equal to 1/2. And we can see that in our calculator. If I take sine and I type in 30, I get 0.5, which is also the same as 1/2, right? Now, the inverse function, what that does is it does the exact opposite. Instead of starting off with 30 degrees, the inverse function, or the sine -1, would take the 1/2. We'd take sine -1 of 1/2, and then that would tell us the degrees, right? So we would do that by hitting second, sine -1, 1 divided by 2, and parenthesis, and then we get 30 degrees. All right? So that's how the inverse functions work. They do the exact opposite of each other. And that's how they relate with sine, cosine, and tangent. Again, we've solved trigonometric problems where the theta was missing, and we would use an inverse function. Like, for example, if we did not know what 60 degrees was, and that was a theta, we could solve this by using cosine. We could say that the cosine of theta is equal to the adjacent over the hypotenuse, right? 1 over 2, right? And then in this case, we would want to separate our unknown, so we could divide each side by cosine. And then from here, we would want to move cosine to the top, cosine having a positive exponent of 1. When we move it to the top, it then gains a negative exponent, so it would be cosine -1 of 1/2, right? And then if I type that into my calculator, I should get the theta, which is 60 degrees, right? So if I hit second, cosine -1, 1 divided by 2, I get 60. Oh, I just realized that's a glare. There we go. So we have cosine -1, 1 divided by 2. We get 60 degrees. It all works out. Now, inverse tangent functions and inverse sine functions and inverse cosine functions all have a very distinct problem. if we were to go on the unit circle and we just wanted to do cosine of 60 degrees, right? We can find that here, where cosine is positive. Well, what other quadrant is cosine positive? All students take calculus. Oh, cosine's positive down here, right? So here at positive 60 degrees, cosine's going to be 1/2 and 1/2, right? And then what if our angle just keeps going? So we're at 60 degrees, we're at 300 degrees, and then we're at 360, and then we're at 420. So at 420 degrees, I'll still have 1/2, right? And if I keep going, and I add another, 360, 300, at 660 degrees, I'll have positive 1/2, and then I can just keep going. And so I can infinitely keep adding degrees, and every time I get to this point and this point, this point and this point, I'll have a cosine of 1/2. So if I want to ask you, what is the arc cosine of 1/2? You've got an infinite number of answers. You're going to have 60, you're going to have 300, you're going to have 420, you're going to have 660, and then it's just going to keep going forever and ever and ever. So we put limits on them. Let me see here. Where are the limits? And they'll put limits on them, and they'll tell you to find the cosine or the arc cosine between 0 and 180 degrees. Or they'll say, just tell me which arc cosine lies between 180 and 360 degrees. So that way you're not putting down all these different numbers. Now here's the other trick with arc sine and arc cosine. What if I tell you to find the arc cosine of, where did it go? 2/3, right? Do we have a reference triangle that has a 2 and a 3? No, we've got one that has a 2 and a √3. Well, remember, cosine is equal to adjacent over hypotenuse, right? And when we do the arc cosine, we're doing the cosine -1 of the adjacent over the hypotenuse. So if the adjacent side of a triangle is 2 and the hypotenuse is 3, I can figure out the other leg. And then once I figure out the other leg, I can actually start using a unit circle to figure out what degrees that is, right? Let me see here. Oh, wait, no, I'm sorry. That hypotenuse is already given. Pause. Okay, I just realized this is taking too long. We're already at 12.5 minutes. We'll talk about these in class, or I'll make a part B video. But we'll talk about what do you do when you have an arc cosine or an arc sine or arc tangent problem that doesn't involve reference triangle distances.